I opened my.
Oh, well, hello everyone. Today we're going to be analyzing something called smooth gradient descent. And then maybe at the end we'll analyze something called subgradient descent. But for now, we'll just start with smooth gradient descent. Okay. So let's start by recalling what the definition of a smooth function was from last time. So a smooth function is a function f. Well, the only property we're going to use, L smooth function today is that it satisfies the following inequality. F of y is at most f of x plus the gradient at f of x times y minus x plus L over 2 y minus x 2 norm squared. So this is the only property of smooth functions we're going to use, so you don't need to know anything else. Okay? And we're going to analyze the natural gradient descent procedure on this function and what type of guarantees you can prove given that. So just what I mean by gradient descent again is the following algorithm. You start at some point x0 in r to the n, and then for t equals 0, 1 onwards, you set xt plus 1 to be xt, and I'm just going to write what the step size is, minus 1 over L times the gradient of f at xt. Okay. So we're going to analyze how well this gradient descent algorithm performs on an L smooth function f with no other properties that we know about the function except for that it's convex. Maybe it's useful for me to write down what property we get out of convexity. No, it doesn't. Convexity is the opposite direction. So it's probably useful to compare these two. So the first line is what it means for the function to be L smooth, and the second line here is what it means for the function to be convex. As you can see, what it's saying is that like you kind of get some lower bound out of convexity, and you get the same bound but plus some extra quantity depending on y minus x L2 norm squared as the upper bound. Again, the goal of today is to analyze this gradient descent algorithm, or at least goal 1 is analyze gradient descent for L smooth functions.
The same elements being the gradient descent.
Yeah. I mean, we'll see later why this choice of 1 over L makes sense, but yeah, it's the same L. Yeah. Okay. Good.
So how much richer is this class of L smooth functions than just like the high dimensional quadratics we were looking at before?
We'll get to it, but for example, L smooth functions, it captures a lot of like other norms that are not just the L2 norm, for example. For the L2 norm, recall that we had a corresponding lower bound where you got some extra plus mu y minus x2 norm squared there, and that's called strong convexity. These p norms will not satisfy strong convexity. They'll only satisfy this weaker notion of just normal convexity.
What do you mean by p norm here, or like a different norm? Because like I was thinking about quadratics.
Quadratics are an L2 norm. Quadratics are an L2 norm under a linear transformation. So you can also look at LP norms. That's what I mean. But quadratics are just an L2 norm under a linear transformation. That is what a quadratic is. Yeah. Okay, good. So this analysis, actually, we're gonna try to go through it slowly, and I think you all will tell me how to analyze it for the most part. So does anyone want to suggest a first step to analyzing this? Maybe think for a bit and then just suggest kind of the first step. Okay, did anyone have any suggestions for like maybe where to start with the analysis? Yes.
Last time, just up or down, the difference between x plus one and f.
Okay. Okay, yeah, good. So the first step that we want to start with is just understanding the upper bound of f of xt plus 1 versus f of xt. This calculation we actually basically did last time, but it's still good to just reiterate what's going on. So if you take this equation for L smoothness and let y equal x plus delta, then you conclude that f of x plus delta is at most f of x plus the gradient of f of x transpose delta plus L over 2 delta 2 norm squared, right? Good. So now for the choice, delta, well, I guess for x equals xt and delta equals negative 1 over L gradient f of x, this equation becomes f of x t plus 1 at most f of xt minus 1 over L. Let me just write it. F of xt transpose f of xt, right? Plus L over 2 times, you get 1 over L squared out of, because delta is 1 over L times that, gradient f, this clearly should be an xt, I guess. Xt 2 norm squared. And then this equals the L2 norm of fxt. So this equals f of xt minus 1 over 2L, okay, times f of xt squared. So we should have already seen this from the last few lectures. But again, the improvement from f of xt to fxt plus 1 is proportional to the L2 norm of the gradient at xt squared, and then times 1 over 2L, where L is this smoothness factor. Now we're going to move on to the next step. But before going to the next step, I did want to introduce two pieces of notation that might be useful for us to, or at least for us to like think about. One parameter that will come up in this analysis is something called what I'm going to call the radius, or r. And here, you should think of r as being the L2 distance between my starting point and x star, where again, x star is the true minimizer of, is like the true minimizer of f of x. So somehow this radius parameter r is going to become important in the analysis, even though it might not be clear right now why it's going to be important. Okay. And the second is just a piece of notation that I want you to find. I'm going to call it the error, or like the optimality error. And I'm just going to let delta of t equal f of xt minus f of x star. So this is just how far in terms of function value is the point xt away from the minimizer of f. Okay. And given this notation, on delta t, this equation up here, f of xt plus 1, and most f of xt minus 1 over 2L gradient f of xt squared can be, well, equivalently written as delta t plus 1 and most delta t minus 1 over 2L gradient f of xt L2 norm squared. Good. Okay. Okay. Now, given this, I wanted everyone to once again think for a little bit on what they might guess that the next step in the analysis is going to be. Sure.
I mean, maybe you want to look at the number of times that you need to decrease the error before the error is like what you would call sufficiently small. It's like the error decreases by some factor
Mhm.
every time. And like, if we understood how many times we need to decrease by this factor.
Sure. So I guess it's good to be more concrete. I guess one goal of the analysis is to understand how many steps it takes to arrive at some delta. I'm gonna write capital T as like the total number of steps and most epsilon, right? So that is the overall goal of the analysis, is to understand how many steps I need to take until delta of capital T is the most epsilon, where like epsilon's my goal error or something like that. Okay. But how are we going to understand how quickly delta T falls to a most epsilon? Well, you need to understand how large like this quantity is, right? So you want to, so like I guess maybe goal 2, you want to understand how large this gradient of f of xt is. So maybe everyone can continue thinking a little bit on how you would try to understand how large the gradient of f of xt is, possibly by relating it to some of these delta terms, if that makes sense. Yes.
I like the max update, right? That, eventually you'll take T steps, but I guess why do you not find also like the lower bound and assume like worst case scenario where like each update is like the absolute like.
Sorry, I didn't catch that. Could you ask again?
Yeah, so like right now I think we're like seeing how large the upper bound is, but do we have to look at how like small the lower bound is to like really see how long it takes? So like if each update takes like the smallest amount possible.
Yeah. That's what I'm trying to get everyone to think about right now, is trying to, so we know that the error is decreasing because the error is going down by like this quantity, but we don't, well, but so far in the context of this lecture where we only have smoothness and no strong convexity, we don't have a way to lower bound how large this improvement is. So if you were able to do that, then you can start reasoning about how fast the algorithm converges. So like, I guess the goal that I wanted everyone to think a little bit about was just, what way could you try to show that this term is not that small by possibly relating it to like delta t or delta, something like that. So maybe just think a bit on how you would maybe try to do that before I continue. Yeah.
Try to upper bound delta zero in terms of R.
Okay. So okay. So I guess one thing is that so let me write this. Let me write it this way. One way you could try to understand is how. One thing you try to understand is how large is delta zero, right? Maybe in terms of R. Let me think if that's actually if that makes any sense. Like what the point of this is you want to understand what the original function error is, possibly in terms of the radius. Do I see how to do that? Might be possible. Let me think about that. This wasn't what I was intending, but maybe I'll think about it while you all generate some more ideas for how to analyze things. Yeah.
Delta 3+1.
Okay. So another approach is you can, maybe approach. You can try to lower bound this quantity 2 norm squared using convexity, right? The idea would be that last time we used smoothness to get an upper bound, and we used strong convexity to get a lower bound on our progress. This time, in the context of this lecture, we no longer have strong convexity, but we still do have at least normal convexity. So perhaps that can be used to give some lower bound on this size of the gradient. Did anyone see a more concrete way to use convexity to get a lower bound on the size of this gradient?
Delta t+1 minus delta t is just f of t x t+1 minus f of x t. And you can apply the convexity of that difference. Right? That's at least the gradient times y of x.
Okay. I think a lot of things were almost correct. So, let me just do it correctly. I think what you said is close, but you don't actually want y and x to be x t plus 1 and x t. You actually want probably y to be x star and x to be x t plus 1 is the problem in the end. Let me just write it out formally. So the idea, once again, is to apply convexity and then use the Cauchy-Schwarz inequality. Let me just write out what all this means. Okay. So by convexity, we know that f of x star. So applying, let me just write it over here. So the lower bound step. So by convexity, we know that f of x star is at least f of xt plus the gradient of f of xt times transpose times xt, my fault, times x star minus xt, right? So by rearranging this equation and flipping some signs, you get that gradient f of xt transpose xt minus x star is at least, let me write in a different order so I have more space. So you have delta t equals f of xt minus f of x star, right? Which is at most gradient f of xt transpose times xt minus x star. Okay. Does this manipulation make sense to everyone? So this is just, we have convexity, and then I'm rearranging this to write that f of xt minus f of x star, which was exactly our definition of the error delta t, is at most this inner product between f of xt and xt minus x star. So now we have this, and remember what our goal was. We wanted to have some lower bound on the size of the L2 norm of f of xt squared. So this is where we apply something called the Cauchy-Schwarz inequality. What the Cauchy-Schwarz inequality says, I guess I have some space here. Cauchy-Schwarz. This is a very fundamental inequality. And what it says is that for any vectors A and B, we have the following. The inner product between A and B, even in the absolute value, norm of A times the L2 norm of B. More explicitly, if I were to write out A is A1 to AN, and B is B1 to BN, then the following inequality holds. A1 B1 plus A2 B2 plus AN BN squared is at most the sum of the squares of the A's times the sum of the squares of the B's. So this is called the Cauchy-Schwarz inequality, and I'm probably not going to prove it here, but it's pretty short to prove. I wanted to continue with the analysis though. Maybe if anyone's interested, at the end of the class, if we have some time, I'll produce a proof of this. But for now, let's just continue with this analysis. Delta t is the difference, which is at most this inner product. And now by applying the Cauchy-Schwarz inequality, because this is positive, then most the L2 norm of this times the L2 norm of xt minus x star. Okay, good. Now this looks quite close to what we want, because the first term is the L2 norm, and the second term looks like some radius term, right? Remember what the definition of radius was? It was the difference in L2 norm between the starting point and x star. Here we have something a little bit different. We have the L2 norm difference between xt and x star, okay? So it would be nice if it were true that this distance was always at most the initial radius r. This is in fact true, but I once again will defer the proof until a little bit later because it's a little bit out of the way. Lemma is that the distance is always decreasing for all t. Well, I mean, this is just a statement. And then by applying this inductively, you conclude that, so by applying this inductively, you conclude that this distance in L2 norm is at most the original distance is at most r. Once again, I will this I definitely will prove soon after I finish the remainder of the analysis, but for now I just want to like not do it because it's a little bit out of the way. Okay. So we've concluded now that this L2 norm squared times this L2 norm times R. Okay. And okay, good. And where do I want to write the last thing? I guess I'll move back over here. So from that sequence of inequalities, we've concluded that. So thus the L2 norm of f of xt is at least delta t over r. Okay. And now by plugging it back into this equation, delta t plus 1 is at most delta t minus 1 over 2L gradient f of xt 2 norm squared is at most delta t minus delta t squared over 2L r squared. So do we see how? Okay. Does anyone have any questions about the derivation up to this point? I'll give everyone a few minutes to just digest things. But yeah, sorry, maybe before that, let me just say what the statement is saying. The statement is concretely saying that the next error, delta t plus 1, is at most my previous error minus the square of the previous error over 2L r squared. That's what it is saying. So this gives you some explicit way that just tells you how the error is going down over time. Yeah, does anyone have any questions about how that equation on how the errors decrease was derived? In that case, let me move on to kind of wrapping up the, I'm gonna call this stage kind of like wrapping up the analysis, wrapping up. At this point, kind of the question we want to study now is pretty clear. We have some initial error. We have some initial error, delta zero, right? And now it undergoes this following recurrence. And like we know that this star holds. And now you just want to ask, for what t does it hold that delta t is at most epsilon? And then if we're able to answer this, then this will tell us how many steps of gradient descent our algorithm must take for the function error at the end of it to be at most epsilon. So we want to understand, so you want to in particular bound t in terms of epsilon. I will do this in, I guess, two ways. The first is more kind of by the book. It's what you see a lot in a lot of other optimization notes. And the second way I would say is like a more flexible way to analyze recurrences that are kind of just like this in general. I think both are useful to see. So I'll do that. And then after we do that, then I will prove this lemma and complete the proof. Eraser. Where did I leave the eraser? There's shit. Idiot. Okay. So the first way to analyze this recurrence, I would call the method clever algebra. And the clever algebra approach is to take this equation. So we know delta t plus 1. And we're going to divide both sides by delta t times delta t plus 1. Okay. Q is 1 over delta t is at most 1 over delta t plus 1 minus delta t over delta t plus 1 times 2L r squared. And now using that delta t plus 1 is at most delta t, which is evident from the definition of the recurrence, you get that, in fact, this is at most 1 over delta t plus 1 minus 1 over 2L r squared, right? Because delta t plus 1 is at most delta t. So this ratio is larger than 1. Applying this, well, let me rewrite this. So rewriting as 1 over delta t plus 1 at least 1 over delta t plus 1 over 2L r squared. So that means the reciprocal of 1 over, the reciprocal of the error delta t is growing by 2L r squared during each step. And by applying this inductively, you get that delta t, 1 over delta t, is at least 1 over delta 0 plus capital T over 2L r squared, which is, you can just throw out the delta 0 term. It actually doesn't help you that much. At least T over 2L r squared. Okay. And by applying, well, by flipping again, get delta T is at most 2L r squared over capital T. So for T equals 2L r squared over epsilon, delta T is at most epsilon. Okay. Did anyone have any questions about this? Maybe while you think of questions, I'll just write down formally a theorem statement that we've proven. Okay. F is convex, L smooth with minimizer X star is argmin X of X. Okay. There's some X0 in Rn. I'm gonna let capital R be X0 minus X star. Now define xt plus 1 equals xt minus 1 over 2L radiant f of xt. Then for capital T equals 2L squared over epsilon, we have that the error is at most epsilon. In other words, f of x t, capital T, minus f of x star is n most epsilon. So far, this is what we've proven is this. Well, minus this lemma, which I do promise to actually prove. Yes, start here.
So what, like, logarithmic in one over epsilon, or near in one over epsilon, I think?
Yes, that's right.
Why not just write it? Like, that you slowed down by losing our limit.
Yeah, okay. So once again, the question was, in previous lectures, when we had strong convexity, the number of iterations it took to get down to epsilon error or something like epsilon error was proportional to logarithmic in 1 over epsilon. And here, the amount, well, the convergence rate was in fact proportional to 1 over epsilon. And okay, the question is, why is that what's happening? Like, why is the convergence rate 1 over epsilon? Let me actually think about whether.
I wanna guess.
Sure.
That, I think it's because previously we managed to like bound like the difference between x star by like a geometric series.
Mhm.
Essentially, because we were able to show that we like decreased by a certain factor every time, and here we only like subtracted by a certain factor every time. So you'd expect that like, you need linearly many times in this factor to.
Sure. So very concretely, in previous lectures, we had a recurrence of the form delta t plus 1 is at most like 0.99 times, is at most 1 minus some constant times delta t, right? And that'll give you a logarithmic dependence. Here we get delta t minus delta t squared, which leads to the 1 over epsilon. But you can still ask, but like even given that, you can still ask more intuitively, why should I have expected this delta t squared to be here? Like, why should it be delta t squared and not delta t when we lost strong convexity? I don't have a great answer for that, but it's a good question, and I'll think on it. Yes.
So, it's that requires knowledge of R, right?
No, right?
But,
It did not. Yes, it only comes into the analysis. R was not required to implement the actual step.
Depends on. Not implementing a step.
Correct. Knowing when to stop depends on R, I suppose. Yeah. But
A different question of the Henry type. So why would we expect dependence on R squared rather than on R? That was surprising to me.
yeah, why are you expecting dependence on R squared instead of R? Once again, I don't actually have a great answer to all of these questions, but yeah.
using a norm squared, right?
Sure. I mean, yeah, once again, there's concrete reasons why it comes up, but what if?
You imagine that you're just walking in like a steady pace, sort of towards the direction.
Yeah, you have to be a little careful because once again, there's like connections between epsilon and R in some weird way, right? Because like,
I actually don't know why.
okay, let's see. Yeah, maybe you're right. Maybe there's not really a reason. Well, once again, these are I'm not sure. I don't have a great answer to all of these. Yeah.
We have a worst case example for.
A worst case example for this kind of iteration dependence, probably you look at like my guess is you would look at something like these like soft max functions that I'll get to in the next lecture, and those should basically hit this. Yeah. Yeah. I think you look at, yeah, I think starting next, maybe in the next lecture, I'll introduce these like soft max functions, and these probably you should indeed be getting things like this and not that much better. Well, okay. For this algorithm, you definitely will get this. You can ask, do there exist other algorithms that beat this? And the answer is yes. That's called acceleration again. But once again, I won't get to that for a while. No.
That's when you increase the step size and you keep going forward.
No, that's not what it is. It's different. Yeah. You like use your previous information to like change the direction you're going a little bit. Yeah. Yes.
I guess we spoke about this a little bit, but
if we don't know L, is there some intuition on like how we could estimate or overestimate? Ls? Like,
Yeah. So good. So if you don't know L, what do you do? What I would do if you don't know L is you can like you can look in the direction of the gradient and you can take the long possible, if that makes sense. Like like a like we have this function, right? Oh, sorry, with the function, and you're currently at xt, and there's some line which is in the direction of the gradient, right? And on this line, the function is convex. You can check that because for any convex function, if I look on a line, it's still convex. So you can kind of just like look in this convex function and find the point that's kind of minimizing it in this direction by doing something like a binary search because it's one dimensional. And then you can just move there, and that probably still works. The analysis should still kind of just work. Because this step size was just chosen to like minimize the upper bound anyway. So like if you're making at least that much progress each time, then you still should be good to go. Yeah. So you don't need to know L. You can just kind of like look in that direction and like try to make as much progress as you can, and that should be good enough. Yeah.
Maybe like another intuition check, like what happens if we just took like steps bigger than this? Like maybe a lot bigger than this.
Maybe delta t wouldn't go down, right? Like for example, if you have a quadratic and you're here, like if I take a small step, yeah, my function error is going down. Take a huge step, I'm like went to the other side, right? So like you can't do that. Yeah. Okay. Good. Now, okay. Before, yeah. Well, let's see what I want to do. Okay. Bef I think actually for the time, I'm going to prove this lemma and then move on to something else. So let me actually try to prove this lemma now. That the distance between xt plus 1 and x star is going down. Now, like, you might think that this seems kind of like obvious because I don't know, like, I'm at some point, x star is somewhere, I'm taking a gradient descent step, like, it would be pretty bad if I'm not like getting closer to the optimizer in distance. But this is kind of a finicky statement. It's like not true. It's like true very much because of the L2 norm. It's like not actually true in like super generality. So I just want everyone to keep that in mind. So this kind of statement is actually a little bit strange. Let me transcribe the lemma there and then prove it on this board. Like, okay, let me put it this way. In later lectures, I'm going to start discussing whether you can do this kind of gradient descent step, but not in the Euclidean norm. So in other norms, yeah. And then you can ask, does this statement still hold in another norm? And the answer is actually no. The fact that the distance is actually just going down every single step is a very particular property of the Euclidean norm, and it's not a property of other norms. But yeah, like for example, yeah, next few lectures I'm going to start talking about gradient descent in other norms because it's useful. Okay. Distance. So the lemma is xt plus 1 minus x star L2 norm is in most xt minus x star L2 norm. This is what we want to prove. So once again, to keep notation nice, I'm going to let delta equal negative 1 over 2L gradient f of xt, right? So what we want to prove then is that xt minus x star plus delta 2 norm squared, where, well, that plus delta is just xt plus 1, is in most xt minus x star L2 norm squared, right? So let's expand out the left-hand side and see what it is. This equals xt minus x star 2 norm squared plus 2 delta transpose xt minus x star plus delta 2 norm squared. And this is like the set that is critically using that we're working in the L2 norm and not a different norm. That you can just kind of actually expand it out and get this equality here. So we went to prove that this is at most xt minus x star 2 norm squared. These terms cancel, and we want now 2 delta transpose xt minus x star plus delta 2 norm squared is at most 0. Okay. Good. So how do we prove this? Let me see. I moved it. Okay. Okay. So I seem to have. I don't have my notes. Let me see if I can actually recover what I'm supposed to do here. Okay. So let's start with the delta 2 norm squared term. Delta 2 norm squared, right, is 1 over. Wait. Is delta? No. There's no factor of 2, right? Did I mess this up? There's no factor of 2 anywhere. Okay. I messed all this up. Okay. I've done this wrong before. Okay. Sorry about that. So in the gradient descent step, there is no factor of 2, right? That is correct. Okay. Also, there should be no factor of 2. Okay, good. So delta 2 norm squared is 1 over L squared gradient f of xt squared, right? Okay. And from before, we have argued that f of xt plus 1 is at most f of xt minus 1 over 2L f of gradient, like the gradient squared, right? This is from before. This was the upper bound. In particular, 1 over 2L, the gradient squared is at most f of xt minus f of xt plus 1, right? So plugging this in, we get that this is at most 2 over L times f of xt minus f of xt plus 1. So that handles that term. Now we want to move on to understanding this 2 delta transpose xt minus x star term. And that term, well, 2 delta transpose xt minus x star. This is equal to negative 2 over L gradient f xt transpose xt minus x star, right? And once again, this time we use the convexity bound, where earlier we argued by convexity that f of, well, earlier we argued by convexity that f of xt, well, f of x star is at least f of xt plus the gradient of f of transpose x star minus xt, which then by rearranging, you get that gradient f of xt x star minus xt is at most f of x star minus f of xt. Okay. So by applying this over here, this quantity exactly equals, well, gradient f x t transpose x star minus xt. This is at most negative 2 over L f of, it's 2 over L f of x star minus f of xt. So now the proof concludes by just summing these two expressions and then noticing that, well, it's just MO0. Let me just write it over here because it's not that, well, I'll just write it over here. Delta squared plus 2 delta transpose x t minus x star is in most 2 over L f of xt minus f of x t plus 1 minus, well, I guess plus 2 over L f of x star minus f of x t, which equals 2 over L f of x star minus f of x t plus 1 and most 0, because f of x star is the minimizer, so it's at most f of x t plus 1. Okay, so that's the proof that the L2 norm goes down. No. Unfortunately, this proof is not. It's a little hard to gain intuition for what's going on in this proof because, as I said, it's not like a super generic property of like convex optimization in general or something. This happens to be just a very nice property that occurs in the Euclidean norm. You know.
If you said that, if you were to say the property in words, it's that you're always decreasing towards the min. Like
In words, when I run gradient descent, that the distance between my current point and the optimizer is going down. The distance, not the value of the function. If that makes like value of the function is like that's kind of obvious in some sense that the value of the function is going down because like the gradient is just telling me the direction to move to decrease the function error. The more surprising property is that the L2 distance to the optimizer is actually also going down. And that's what this proves. But as I said, this is a lot more unintuitive. Yeah. Okay. Let me see. 1 second. Okay. Okay, does anyone have any questions about this? If not, I'll move on to like, well, yeah. Okay, let me give everyone a few minutes to think if they have any questions about anything. This is all I wanted to say about smooth gradient descent so far. Anyways, okay, I'm gonna raise some stuff. Please let me know if you have any questions. Probably in the last little bit, I will cover something called subgradient descent, which, well, I want to cover it at some point because I think the analysis is interesting, but I wasn't sure exactly when. So let me try to do it. If I don't succeed. Uh, you don't need to worry about the word subgradient. Really, the goal of okay. Anyways, okay, so like we're gonna switch gears for the last like 25 minutes of the lecture and talk about something called subgradient descent. This is really kind of like a one-off thing, but I do think it's important that everyone sees this style of analysis at least once. So the idea in subgradient descent is that, well, we're going to try to make like very few assumptions on the function, see what we can prove anyways, okay? So really, in this, the only assumption we're going to make on f, so the only assumption we're going to make is that the function f is convex. And the second assumption is that the function f is Lipschitz. And here what Lipschitz means, there's equivalent notions of Lipschitzness. The first is that when x and y are close, the function value is close. G is going to be the Lipschitzness constant. So this is our assumption on the function f in this lecture, Lipschitz, in this section, Lipschitzness. F of x minus fy is at most g times x minus y L2 norm. Equivalently, the L2 norm of the gradient at any point is at most g. These are equivalent.
This is the stronger assumption. It assumes it's like differentiable.
Yeah. That's right. Like if it's not different, like in the notes I've written for this lecture, I'm not assuming it's differentiable. You don't need to, but let's just assume it's differentiable. You really lose very little by assuming it's differentiable. And here's the goal of what we want to prove. Okay. Let's see. So you start at, so we have this function f. It is G Lipschitz, which means it satisfies properties we've defined. Convex. Now, given x0 in Rn, again define the radius r to be x0 minus x star in L2 norm. And now define the following sequence of gradient descent steps. Xt plus 1 is xt minus eta times the gradient of f of xt. Okay. Find x bar to be the average point encountered on our path. This is a little bit strange, but bear with me. Okay. So x bar is the average point encountered in the gradient descent steps. Then f of x bar is at most f of x star plus the following bound on the error, which is r squared plus 2 eta tg squared. No, this is wrong. What is it? R squared plus eta squared t g squared over 2 eta t. Okay, that's the correct bound. So the guarantee is a little bit weaker. So in what sense is it weaker? In previous analyses, we were able to say that as you take more steps, I get closer and closer to x star. On the other hand, here, you don't really get that. You kind of just get that on average, like I'm kind of close to x star. And it's not true at all times. I think this is kind of necessary, basically. You can't get around this. Okay.
So like just to concretize like which kind of functions we're thinking about, is there like example of a function which satisfies this weaker assumption but not our previous like smooth assumption?
I think just kind of like Lipschitz just means that like it can't be growing too quickly anywhere. So you can kind of just like take a bunch of like linear functions or something and then take their max, I guess, and it's going to be convex. And as long as none of the linear functions is too high a slope, then you get something like this. Okay. But anyways, we're going to try to establish this. Maybe before I do that, notice that there's actually two parameters I'm allowed to set here. I'm allowed to set the step size t, and I'm also allowed to set this parameter eta, right? Eta is the step size.
Yeah.
Yeah. But like I can choose the step size to, if I have committed to how many steps I want to take, I can choose eta to try to minimize this expression. So let me just do that calculation. Eta squared t g squared over 2 eta t. This equals, well, okay. I'm going to just tell you what the setting of eta is. Eta is going to be r over root t times g. And then if you do the calculation, what this will equal is 2r squared over 2 eta t is r squared over eta t, which is, what is it? Rg over root t, I think. So when eta is chosen like this is your error. So the error decays as 1 over square root t. But once again, notice that this error is not like for every point. This is on average, like the average point, the error is 1 over square root t. It's not true for every point. And let me quickly do this analysis. Now, this analysis is going to look a little bit strange because it kind of has to fall outside the scope of what we've looked at thus far, because we kind of have no means at all of establishing any reasonable upper bound. Like, we just don't have any like upper bound on the function f. Like, sorry, we have no way to argue that xt plus 1 has a better function value than xt. So kind of the analysis basically just has to look quite different. Instead, the idea in this analysis is to use the distance to opt as a potential function. As a potential function. A little more, the idea is to do this. And this ties in kind of nicely to the proof over here. Because in this proof, we have literally just computed what is the difference between the distance of xt plus 1 to x star and the distance of xt to x star. So that's maybe one way you would motivate trying to use that as a potential function. A little more concretely, let me do this over here. I'm going to again let delta equal negative eta times gradient f of xt.
If your function is not differentiable, how do you know in which direction to go?
Convex functions have a thing called subgradients at least. And a subgradient is kind of like a direction that obeys the same lower bound as a convex function. Like a convex function satisfies this, right, if it's differentiable. Right? So a subgradient is just any vector g which depends on x, which satisfies that. Then this is called a subgradient. So like you can use subgradients if you want, if the function is not differentiable. I don't know. I mean, theoretically, I don't think you really see the difference, but yeah, in practical settings, I wouldn't know. Yeah. Anyways, let me get back to this. Delta is that x t plus 1 minus x star 2 norm squared minus xt minus x star 2 norm squared equals xt minus x star plus delta 2 norm squared minus xt minus x star 2 norm squared. This is really identical to the calculation being done over there. Equals 2 delta transpose xt minus x star plus delta 2 norm squared, right? Okay, now just as we did over here, for this 2 delta transpose term, we are going to apply convexity to get what we want. And then for this delta squared term, we're going to apply Lipschitzness to get the bound we want. Let me just write both of these out. It's going to be negative 2 eta gradient f of at xt times xt minus x star, okay? And then plus eta squared gradient 2 norm squared. In the first term, we're going to use convexity, and it's almost 2 eta times it's negative 2 eta f of xt minus f of x star. This is by convexity. And the second term, by the definition of Lipschitzness, all gradients in the L2 norm are most G. So this is plus, this term is bounded by eta squared times G squared. So what is this saying? This is saying that if my function value is far away from opt, like if my function error is large, then this tells me that I'm getting closer and closer to x star. This is what this is. So maybe intuition. If f of xt minus f of x star, which is the error, is large, then the distance decreases. Right? And the distance can't just keep going down because it initially starts at r. It just can't keep going down. So that means that on average, the error can't be that large. That's really all the analysis is going to say in the end. So let me just formally.
We're not strictly moving towards it because this like eta squared g squared.
Correct. You're not strictly moving towards it because of the second term, but this can't be too large too often, or else my distance, it will just keep going down. So that just can't happen. So to formalize this, all you do is, well, you sum this equation from t equals 0 to t equals capital T minus 1. Sum from t equals 0 to capital T minus 1 to get. When you sum this, every intermediate term cancels except for the last one and the first one. So you get xt minus x star 2 norm squared minus x0 minus x star 2 norm squared, right, equals negative 2 eta sum t equals 0 to t minus 1 f of xt minus f of x star plus t times eta squared g squared, right? So just by rearranging, and most, I guess. So by rearranging, you get sum t from 0 to t minus 1, f of xt minus f of x star, at most, t eta squared g squared. Do we put a 2 eta here? T eta squared g squared plus x0 minus x star squared minus xt minus x star squared, which is at most t times eta squared d squared plus r squared. And now we're almost done because all we want to do is compare f of x bar to, well, this sum over here somehow, right? If you can compare x bar to that, then we've completed the proof of the theorem. And that just follows because f of x bar equals f of 1 over t sum xt, t from 0 to t minus 1, which is at most, by using that f is a convex function, 1 over t sum f of x t, t from 0 to t minus 1. Okay. So now if you just plug this into here and then divide both sides by 2 eta times capital T, then that concludes the proof. I'm not going to write it out because I think the formulas are getting large enough, but plug in and then divide by 2 eta times capital T to conclude. Okay. Maybe once again, I'll ask if anyone has any questions about the analysis of this part. Once again, the idea is, because we don't have any way to like directly argue that the function value is decreasing, we resort to using this L2 distance as a potential function. And exactly by, well, I guess I erased it, but the analysis that we did earlier, you get two terms. You get the first term, 2 delta transpose xt minus x star. You get a delta 2 norm squared. The first term, we use convexity to relate it to the function error. And in the second term, we just use Lipschitzness to bound it by g, which is the Lipschitz constant. And then, well, then you get a telescoping sequence out of this, and then you will rearrange a little bit and you get what you want. So, well, that's all I wanted to talk about today. If anyone had any questions, that'd be great. Yeah. Good. Well, in note, it's called subgradient descent because technically in this theorem, you could have replaced this with any subgradient and the proof works identically. Yeah. Yeah. Note, you could replace this gradient f of xt with any subgradient at xt. And the proof works identically. Yeah. Yes.
Question on like the x bar, so like
Yeah.
since x bar is an argument of f, what is like a summation of the function value?
Oh, that's horrible. Oh, thank you. Okay. Good catch. I completely missed that. It should be the average value. Yeah. It should be 1 over t times sum of xt. Another way you could also look at this is like you could say like, if I keep running this, then the best value I find at some point is at most within that error. You don't need to look at x, y. You could just say the best value I've encountered so far is within that error. Yeah. That also works.
I mean, there must be some loss between your average value and your best value.
Average value, best value is always at both. F of x bar is always at most. Well, by convexity, when I average a bunch of points, the value only goes down, right? Okay, well, that's all I had. Okay, see you all next week, I guess.